All right, hey everybody, thanks for coming to the EERI seminar. Today we have Satish Manandhar. He's a postdoc here with us in geotech. He got his bachelor's in Nepal in 2012, and then later went to South Korea to get his master's and then stayed for his PhD, specializing in geotechnical earthquake engineering. Before his PhD, he also did offshore foundation projects for wind turbines for the Korea Electric Power Corporation. And overall, his research goals are to advance the performance and evaluation of geotechnical systems and infrastructures during earthquakes. So without further ado, take it away.
Okay, thank you. Good afternoon to everyone. Thank you, Noah, for the kind introduction. And thank you to the EERI student chapter for giving me an opportunity to present today. Also, I'd like to thank the audience member for taking the time to be at the seminar, and also the people who are in Zoom watching this live. So I'm going to talk about my research, which I'm doing as a postdoc for the past 1.5 years, which is on the effect of bidirectional earthquake shaking on nonlinear site response analysis. So I'm working with Dr. Motammed, who is the PI on this project.
You click on the right monitor. I think that will work. Use the mouse to click on the right monitor.
Oh. Yeah, sorry for that. So first of all, I would like to acknowledge the financial support provided by the Department of Energy. And this work was done in collaboration with the Los Alamos Test Laboratory. So with regards to the contents, so I'll be introducing my research, and then we'll talk about some of the Elestina modeling for this, and then the selection of the input motions, and comparison of 1D and 2D shaking results, and then conclude with the conclusions and provide some next steps. So the introduction. So when there is an earthquake, so seismic waves, they propagate from the fault rupture through the Earth's crust, and they arrive at a recording station, which is usually at the rock outcrop. Usually we don't get the bedrock, we don't record the bedrock motion. So what we do is that we deconvolute the motion at the outcrop to get the bedrock motion. However, our interest of motion is the surface motion on the soil because we have our structures on top of the soil in most cases. So the site response analysis is basically a numerical procedure which takes the bedrock motion and propagates this motion in the form of shear waves through the soil layers, considering their properties, and then get the surface motion. So usually the surface motions are typically amplified because the soils are much softer than the rock, right? So this is the case when the damping is very low. And we use this amplified surface motion as an input to design our structures. So in the current site response analysis practice, what we are doing is we are using a one-dimensional model as shown here. So this is a soil column model. Typically, we use programs such as shake or deep soil to do this. And with regards to the earthquake motions, so usually the earthquake motions are recorded as 3 different components, usually with 2 horizontal, H1 and H2, and 1 vertical component. So here is the acceleration time history for the Loma Prieta motion recorded at the Gilroy station. So to do the site response analysis, what we do is that we take the individual components of this motion and then input it at the bedrock as a one-dimensional shaking. So with this, we can get the response at the surface, HS1 or HS2 for each of these components. If you want, then we could also combine these components using geometric mean or some other factors. So the problem here is that Here I have shown an orbit plot for the shaking in x direction. So here you can see the x acceleration on the x-axis and the y acceleration on the y-axis. So if you take the orbit plot of this x direction motion, you will get a straight line, which is parallel to the x-axis. Which means that if you model a full column, it will move in that direction, right? Only in the x direction. However, if you take a motion and then use the x and y acceleration simultaneously, then you will get a plot as shown here. So the motion of the column will now be in an xy plane rather than only in x direction. So we have a multi-directional loading now. So the research question is, what is the difference in soil response when we do a unidirectional or 1D shaking versus a 2D shaking? So to understand the effect of the biaxial shearing, so first of all, let us consider a hypothetical case in which the x and y motions are equal. So here you can see the time history for the low Marketa motion, in which the x and y acceleration are the same. If you plot the orbit plot for these motions, then what you get is a straight line, which is inclined at an angle of 45 degrees with the x-axis, which means that the soil column will move in this inclined direction now, right? So if you were to calculate the resultant acceleration for this resultant case, then we would simply get, because it's x and y is equal, so we will get √2 times the acceleration in either x or y, which means that if we do bidirectional shaking, we are getting 41% higher spectral higher acceleration than if you do it only in one direction. So this higher acceleration will translate to higher shear stress, and it will increase the shear strain. So in the soil, if you increase the shear strain, what happens is that there will be some nonlinear effect. Mostly, the shear modulus will decrease, and it will also increase the hysteretic damping. So if you look at an actual case now, instead of the hypothetical case, in which the x and y motions are not the same. So this is what happens typically. So in the time history plot, you can see that there is some difference in x and y acceleration in terms of both amplitude and phase, right? So this is what causes the acceleration trace to look like this in the orbit plot, right? So this shows that if the soil is moving as described by this acceleration plot, then we are subjecting the soil to a multi-directional stress path. And now the response of the soil, it depends on the nature of loading. So there are not many studies that I've done with regards to bidirectional shaking effects. So this is one of the earliest studies that was done by Yamada and Chihara in 1983. So in this study, what they did is that they took a soil sample, and then they subjected that soil sample to in a bidirectional simple shear apparatus to different stress patterns. So like circular path, elliptical path, and some of the crisscrossing paths. The objective was to look at the liquefaction resistance of that sample, which is saturated under undrained condition. So here you can see the graph of cyclic stress ratio versus the number of loading cycles. And also you can see a number of lines for different stress paths. This indicates the liquefaction resistance curve. So if you take a given number of cycles, for example, in this case, I've shown as 3 cycles, then if you have a unidirectional shearing, then you would require a higher shear stress to cause liquefaction, as compared to when you use a circular stress path, right? So this means that if you have a bidirectional shearing, then we will lower the resistance of the soil.
I messed it up, my bad. Go ahead.
So the next study is more closely related to my research. So this was done by Dr. Mohammed in 2016. So here the authors, they used the recordings at an instrumented site in Japan during the 2007 Shetsuki earthquake. So here we have a site which is around 100 meters deep, and also there are a number of layers. The good thing is that they have instruments at these sites to record these motions at different depths. So ST1, ST2, and ST3 are the accelerometers. So the authors, they created this model in LS China using a soil column. And then they compared the spectral acceleration versus the period for the recorded motion, for the predicted motion using 2D shaping and predicted motion using 1D shaping. So you can see that the predicted motion, 2D shaping, which is shown by the red line, is much more closer to the black line, which is the recorded motion, as compared to the blue line, which is the predicted motions in 1D direction. So this shows that 2D shaping results are much more closer to reality than 1D. So with this, I'm going to state my research objectives, which is to evaluate the effect of bidirectional earthquake shaking on site response analysis using LS China. So I plan to consider a large number of motions to take into account the different nature of loadings and also the soil columns of different heights. So this is the focus of this presentation. There is another objective for our project, which is to validate the effects of 2D shaking using the large-scale shake table test, as you see shown here. So moving on, so I will describe some details about the LS China modeling. So I created 3D soil column models in LS China. So I used 3 models. The first model M1 had a height of 4.5 meters and had an elastic site period of around 0.1 seconds. The model M2 had a height of 36 meters and a period of around 0.5 seconds, and model M3 had a height of 90 meters and period of 1 second. Some of the features of these models is that the nodes, which are located at the same height, so they are constrained to move together in shear. So we have only translational motions and we don't have any rotation. And also the earthquake motions, they are applied at the base as acceleration time history, meaning that the base is rigid. As for the soil property, so the soil we are trying to model is a well-graded sand. It has a dry density of 1858 kilogram per meter cube with a unit weight of 18.53 kilonewton per meter cube. The void ratio for the soil was around 0.426 and the relative density of 71%. The friction angle for this relative density was around 40 degrees, which was found from the direct shear testing, and the cohesion was 0. So using the empirical relationship by Seed et al. In 1970, we can calculate the maximum shear modulus for the soil at different depths using this equation. So if you have a void ratio and if you know the mean confining stress, then you can estimate the Gmax. If you know the Gmax, then you can estimate the shear wave velocity. If you know the density, which is already there. And also we calculated the shear strength of the soil based on the friction angle. So the plot here shows the VS profile and the shear strength profile with respect to the normalized depth. So Z over H, here H is the height of the column. So this is shown for all the 3 models, 1, M2, and M3. So moving on to describe the constitutive model for the soil. So I used the math hysteretic soil model in LS China, which is also called MAT79. The reason I use this model is because this model can consider 3D stress state. That is what we require to understand the bidirectional shaking. And this model is described as a nested surface model. So you can see that in order to define the nonlinear stiffness and yielding, we have this user-defined backbone curve. So we define it by ourselves with a user input. And based on this, the program makes a number of perfectly elastic surfaces based on the number of points we define. So in this way, you can consider the like a curved path, curved user-defined curve like this. As for the hysteretic damping, leading rules for loading and unloading. So here you can see for different strains how the damping evolves. For the dynamic fluid properties, as I said before, we need to define the stress strain curve. So this was done based on an empirical relationship by Darren Daly, 2001. However, the issue of defining stress and strain using Darren Daly is that it is not corrected for the shear strength and larger strains. So what I did is that I used this modified two-stage hyperbolic model to correct the strength of this stress strain curve to the correct shear strength of the soil. So here this response is for model M1 at layer 4. So we could do this for all the layers. And based on this stress strain curve, we can define the shear modulus reduction curve and also the damping curve. The issue here is that the damping curve we define from this stress strain relationship is based on basing damping, which gives a very large damping at larger strains, like 1% to 10%. So I modified the damping to non-basing damping, which is much more closer to the empirical relationship. So in addition to the hysteretic strain curve, we need some small strain damping, right? Because if you don't that, then there will be no damping at small strains. So the D minimum was calculated based on Darren Levy 2001, and a constant value was maintained in the frequency range of 1 to 30, which is the frequency range for our response. And this damping was maximum near the surface and it decreased with depth. So you can see for models M1, M2, and M3, we have 1% at the surface and it decreases with depth. So since the height of the column is different, so we have different values. So with this, I will move on to the selection of the input motions for performing type response analysis in Palestina. So to select the input motions, the first thing I did is the disaggregation of seismic hazard. So basically, I used two different sites. So here I have shown a site called NANO, which stands for the Los Alamos National Lab site. So here is the location of the site in New Mexico. So you know that New Mexico is a low to moderate seismicity site, right? And you could see also the location of faults near the site. And on the right, you can see the disaggregation results. On the z-axis, you can see the contribution to hazard, and on the x and y-axis, you can see the rupture distance to the fault, as well as the earthquake magnitude. So this is for our earthquake return period of 2475 years. So in disaggregation, what I did is I selected the column with the tallest height, the tallest column, which corresponds to the certain magnitude and certain fault rupture. So you can get that magnitude pair contribution using this result. So I repeated this for 3 different return periods, so considering the different level of hazards at the sites. So for the intensity measure, I used the spectral acceleration at the site period of the soil column, which is around 0.1 seconds. And I assumed that site class to be DC boundary, so this one. And one, magnitude of earthquake and fault distance, and this error term is the output from the disaggregation analysis. Do you understand what the magnitude and the fault rupture is? This error term basically means that this intensity measure is like, for example, for this case, like 0.61 standard deviations smaller than what is mean predicted for this magnitude and this rupture distance. So it basically gives you the error in the prediction. And then I selected another site. So now I've selected the Lawrence Livermore National Lab site. So this site is now in California. So this is in the region of high seismic hazard. So here also you can see the fault locations and the disaggregation results for an earthquake return period of 2,475 years. So using the same procedure, I was able to get the magnitude, distance, and this error term for different return periods with spectral acceleration as at 0.1 second as the intensity measure. So this one, I did it for the first model, model M1. So for model M2 and M3, also the process is the same. The only difference is that instead of 0.1 second, I use 0.5 second as the spectral acceleration value and 1 second for model M3. Now also you could assume that the site class would also be different for these models. So once we have the disaggregation results, then we can define the target spectra based on any ground motion model. So I use the Campbell and Bozorgnia 2014 ground motion model. And using this target spectra, I selected 20 pairs of ground motions from the PRNG OS2 database based on the conditional main spectrum method with the conditioning period, which is equal to the full column. So this is done for each return period. So this is the result of selection. So here is the spectral acceleration versus period. The blue lines are what the target median response spectra and the target variance, 2.7 to 97.5 percentile response spectra. And since this is a conditional mean spectrum method, we have the least variance at the conditioning period. The red line shows the median response spectra of the 20 selected motions, which are shown by the gray lines here. And you could see that these motions all they lie within the confidence bounds for the target spectrum. So it's a good thing. So with this procedure, so the initial number of motions that I selected for each soil model was around 120. So this is based on 20 motions which were selected at one return period. So we have 3 return periods, and at one site we have 2 sites, so total of 120. If we include motions that are recorded on data abutments and also some of the motions that are repeated between these models, then we would get around 97 pairs of motion for model M1, 95 for model M2, and 105 for model M3. Now you can also see the magnitude, for fault rupture distance and the VS30 of the station, the range value for these selected pairs of motion. So in total, I did the analysis for 297 unique motions. So now moving on to the results. So I will present the comparison of the 1D versus the 2D shaping results for all of these motions. So before that, I'll just present a brief overview about how I'm going to present the results. So for 1D shaping, we have an X direction and Y direction shaping that is applied separately. So you'll have a response 1dx and 1dy. Whereas for 2D shaping, the X and Y are applied simultaneously, and we have a response 2dx and 2dy. So here I compare the responses in terms of the spectral acceleration at the soil surface and the shear strain profile for the soil column. So those are my response variables. And I compared 1D versus 2dx and 1dy versus 2dy. So first, I will present the results of 1D versus 2D shaping at different PGAs. So for this, I averaged the response of the first model, model M1, to 3 earthquakes. This is Chichi, Parkfield, and Christchurch, which were scaled to different PGAs, just to see the effect of PGA. So here is the result for the shaping in the X direction. The top 3 figures are the spectral acceleration versus period at different PGAs, and the bottom 3 figures are the depth versus the maximum shear strain at these 3 levels of PGA. You can see that the 1D motion is shown in black, whereas the 2D motions are shown in the dotted red lines. We could see that for the lower intensity of shaking, both 1D and 2D motions are nearly similar. But once we increase the level of shaking, we can see that the 1D motion is predicting higher spectral accelerations as compared to 2D motions and 2D shaking. However, in terms of the maximum shear strain, we can see that 2D shaking is producing higher shear strains in the soil column compared to 1D shaking. So if we see this response now in the perpendicular y direction, we'll get a similar story. Right? For lower shaking, they are almost equal. When we increase the intensity of shaking, then we see differences. So the key point here is that 2D shaking will produce larger shear strengths in the soil column. So that increases the nonlinear soil response, which is it decreases the shear modulus, and at the same time, the damping of the soil increased. Because of this increased damping, we are seeing reduced spectral acceleration at the soil surface. So to analyze all of these motions, so I tried to see the difference between 1D and 2D motion in terms of the log ratios. So ratio of the spectral acceleration and the ratio of the maximum shear strain. The reason is easier to compare. So if this ratio is positive, which means that 2D numerator is greater than denominator, so 2D is greater than 1D. If it is negative, then the opposite, and if it is zero, then we are seeing no difference. So this is the response for model M1. So here we have on the left is the log spectral ratios, spectral acceleration ratios with respect to period. On the right is the normalized depth versus the log maximum shear strain. So this is for all the motions in model M1, which is 97 motions. You can see on these faint lines, those are the responses for all of the motions. And also you can see the mean curve, which is shown by this black dotted line, and also the plus minus 1 standard deviation by this the black dotted line. You can see that for this model M1, this is the period of the soil column, which is 0.1 second. So below this period, we are having a log values of around negative 0.1. We are seeing those differences, and then this difference it decreases as you increase the period, and it becomes zero for higher periods. So this is the trend we observe based on many motions. In terms of the shear strain, at the depth, there is a smaller difference, but if we move towards the surface, then we are seeing a log difference of around 0.25. So if you convert this log difference in terms of percentage difference, so on the mean value, we are seeing around 10% difference between 1D and 2D shaking. And if you consider the standard deviation, that's around 25% difference. And in case of the shear strain profile, it translates to 27% difference. So if you see the response now for the model M2, here also we see the similar story. So below the period of the soil column, we have a constant Ln value of around negative 0.05. And we see some interesting observation. At deeper depths, we don't see any difference between 1D and 2D shaking. And all of the difference is for that. This is for a taller soil column. So if you look at an even taller soil column, which is around 9 meters high, the period is around 1 second. So we see very similar difference and also similar results for the maximum shear strength. So what these results show that in addition to the PGA or the intensity of shaking, our difference in 1D and 2D soil response also depends on the period of the soil column. So yeah. So now I will try to correlate the difference in spectral acceleration between 1D and 2D shaking with different intensity measures, so as to have a predictive relationship. For that, I calculated the root mean square difference between the spectral acceleration in 2D minus the 1D. So this was summed at all the periods between 0.03 to 5 seconds. So we are converting a vector value into a scalar value, which is the root mean square difference. And this scalar value is then correlated with the different intensity measures of the phase motion. So the intensity measure I used is the peak intensity measure, which is the peak ground acceleration, the spectral acceleration at the period of the solid column, and the peak ground velocity. As for the cumulative intensity measure, I used the area of intensity, the cumulative absolute velocity, and the Hausner intensity. So this is the correlation results of the root mean square difference in spectral acceleration versus different intensity measures. So this is for the model M1. So on the y-axis, we can see the root mean square difference, and x-axis are different intensity measures. So each of these points represents one earthquake motion. So there are 97 points for model M1 in each of these plots. And to determine the correlation between these points in x and y, I calculated the Spearman's correlation coefficient, RS. 0.8 to 1 indicates a very strong correlation. And also I fitted a hyperbolic curve through this data, and then calculated the goodness of fit, which is described by the R squared value. So you can see that if we increase the intensity of motion, so basically if we increase the value of these intensity measures in the root mean square difference, which means that the difference between 1D and 2D shaking is increasing as we increase the intensity of our shakings. That's the first point. And you could see that the PGA has the highest correlation coefficient, and also the hyperbolic fit is well fitted to this PGA data. So we have, so for this first column, I would say that the PGA is a good predictor for the effects of 1D versus 2D shaking. So if I do this for model M2 and M3, and I compare the RS and R squared values for this model for different intensity measures, we could see that for the PGA, the RS is almost 0.95, R squared is 0.86. However, for the taller solid columns, these are not that good predictor. It's slowly, the values are decreasing now. Whereas if you look at the RS intensity, stays quite consistent, even though it slightly decreases for the model M3, which is around 90 meters tall. So in this case, yeah, I could say that the RS intensity is a better predictor if you are considering any solid column. The other intensity measures, they give some intermediate results. So with this, I will move on to conclusion and my next step in this research. So the key takeaway from this talk is this first point. The 2D shaking, it produces larger shear strengths in the soil. So which will increase the nonlinear response. Specifically, it will increase the hysteretic damping, and this will reduce the spectral acceleration at the ground surface. So this is the key observation from this research. So based on the large number of motions, I found that on average, 2D shaking gives 10% smaller spectral acceleration at the surface than 1D shaking, and it usually at periods below the side period of the solid column. You may argue that 10% is not, but if you consider design acceleration, if you can reduce it by 10%, it can translate to a very significant saving in cost for seismic design. So there is some area here. And also the difference between 1D and 2D shaking is increases with the intensity of shaking, as we've seen with different intensity measures. And the root mean square difference in spectral acceleration has a very strong correlation with PGA for the shorter solid columns, and the RS intensity if you consider all the solid columns. So my next step is doing the shake table test, which I already did. So part of it I already did. I will do it one next month. So the objective is to validate the effects of 2D shaking using a large scale shake table test. So basically we have a soil box, as you can see, which is around 15 feet high, and the width is 21.5 feet. So this is the soil model, which is inside this box. And this box is on a shake table, which can shake in X and Y directions. This box is called the laminar soil box because it is made up of rings rather than being rigid, so the rings can move independently and is supported by bearings. And the soil we are using is a well-graded local sand that was locally obtained and in a dense configuration. So for this first model, I used like 288 tons of soil in this box. For the preparation method, I used the compaction method to compact the soil. So I did that in 66 lifts. So dumping the soil and compacting was done in 66 lifts. The average density I obtained for this soil model is around 105 pounds per cubic feet. And there were a total of 60 sensors that were there, consisting of 21 MEMS accelerometer, 6 piezo accelerometers, 10 string pots, 19 Nova Technique displacement sensors, and 4 spatial sensors. And the shaking is in unidirectional as well as bidirectional. So just a brief overview of the model preparation procedure. So we loaded the soil into this hopper using a loader. And then using this overhead crane, we bring the soil inside the box and then try to spread it evenly as possible. So the help from the staff was very grateful in this process. So although we try to spread the soil evenly in the box, there are still some valleys and troughs that forms inside it. So we have to manually spread the soil. So here is a picture of an undergraduate student who was helping me. And here's a picture of me who is doing the compaction. And during this process, we also embedded many sensors in the soil. So you can see the MEMS accelerometer and the piezo accelerometers and also the earth pressure cells. The accelerometers have to be covered to protect it from the impact as well as from other elements. And for quality control, what we did is that we performed fan cone testing as well as nuclear density test in the soil model. So for the sand cone test, I did 22 different tests at different heights to check the density as we prepare the model, and also cross-correlated with the nuclear density test results. So I'm going to show some shaking videos for 1D and 2D shaking. So this is the Baja California motion at CP station. So the left one is 1DX, so this is the X direction. And the right one is the 2D, so this is the Y direction and X direction. So yeah, let's see this video. I try to time it so that it moves together, but there's like some gap. But anyways, what you can see visually is also that the 2D shaking is kind of, the 2D shaking is making some like kind of rotates the dimensions, you can see that, whereas this is just moving in this direction. And also the intensity of the shaking looks much more larger when you shake it in 2D compared to 1D. So with this, that concludes my presentation. Yeah, thank you all for being here.
All right. Thank you so much for the presentation. Has anybody got any questions for Satish?
Thank you so much for the presentation. A question about the numerical model that you used for the simulating the 2D behavior. I believe that once we had actually a person who came from Schnabel, they were working on a special type of numerical model on Einstein, which was developed by Yusuf Hashash and those people. Have you compared your model that you're using with their model and to see which one behaves better than the other one, or no?
Yeah, thank you for your question. Actually, we already did that. So I got that model name is called iSoil. So I contacted Professor Alsas to get that model, and I compared the response from this matte hysteretic soil with ice soil, and we got very comparable results. Yeah.
Any other questions? Press and hold the button.
When to press.
Yeah.
Thank you for the presentation, Satish. I have a question regarding the modification that you have done for Darren Dolly. So can you elaborate more about that modification and the drawback that you mentioned about overestimation of tau max? Is it something that's reported by other studies, or you just see it in your case?
So for your first question regarding damping, so you can see that the masing damping, if you use, especially on larger strains, we are getting around 50% damping, whereas the empirical curve is only showing 20%, right? So in the previous version of Palestina, we could not use the non-masing damping. Like we have to rely on this masing curve, which will basically over predict our damping. However, in the new version of Palestina, I think for version number 14, we could use a non-masing curve. So basically what it does is that this stress strain loop, the Palestina automatically shrinks this stress strain loop to make the damping smaller. That's how they implemented the non-masing damping in Palestina. But there's no any equations or something like that. It's just, yeah, they say that they do it like this. And for case of the maximum shear strength, generally, people don't do that correction for maximum shear strength because most of the earthquake response, the shear strengths are mostly at this range. We are not there. Most of the response don't do more than 1% strain. So it doesn't make that much of a difference if you don't do strength correction. However, our objective for this research was on nonlinear soil behavior, especially at larger strains. So we had to do this strength correction just to get this strength value correct the larger strains.
Go ahead, Mustafa.
In your last slide about your next steps that you're going to do on the soil blocks, the sensors that you put around, actually the things that was shown on the picture, have you considered the effect of the box itself to the soil and to the sensors? Because I guess that in the center of the soil, it would be much more comparable to the soil response analysis that you do, but in the boundaries, near the boundaries, the effect of the box could be problematic.
Yeah, that's a good question. And actually, I did not show the schematic of how I put the sensors, but actually there were 7 sensors at the center at different heights, and there were another 7 sensors near the edge, like 1 feet away from the boundary, and also there were 7 accelerometers on the box. So we compared the response at the center, near the wall, and also on the wall. So we tried to see the spectral acceleration for these different cases, and actually we got very comparable results, meaning that this biaxial box is working properly to avoid the boundary effect. But I need to mention one thing. You can see in this video, I'll play it again. You can see that the top 3 rings are moving a lot compared to the bottom rings, right? The reason for that is we don't have soil here. So that's one of the things that we try to improve on our next test. We will try to fill the whole box with the soil. So now this on-field frame is affecting the response of the soil also. So there's a slight error right now, but in the next test, we'll try to fix that.
I think we got time for another question or two if anybody's got it.
I have no ways.
No, that was not you, that's the door. I do have a question about, for the soil box in general, my understanding was that one of the potential tests would be to like put a mass on top of it and then check soil structure interaction.
Yeah.
Is that part of this research or is that future
Yeah.
steps or somewhere else?
That's, I believe Reza would be doing it in the soil after me. So I will do one more test and then next test, he will use some concrete foundations, I believe. Yeah, on the soil.
On the similar note for you and or Reza, are there plans to have like two different soil types for like sand to a softer clay at the top, or is it gonna be pretty homogeneous for future testing?
For future tests, we are still using the same soil. Because if we are looking at soil structure interaction, then it's better to have the same soil and then check the response of the structure. But maybe in future tests, then we could have different layers. But for the purpose of this study, we just require uniform soil and it's much more easier to and make it.
Alright, any other last questions? And my nose has alerted me to food, so I assume it's the same for you. All right, well, everybody, let's give one last round of applause for Sadiq.